Okay. So as you all know, I'm following this book, the eighth edition for all the chapters in this course. And the slides also pretty much I've taken from here itself. This is for everybody's convenience, as all of you are, not on campus. So let's move on to the network layer and its functionalities. Until now, we all have studied only about just an introduction to the networking, application layer protocols, and network layer protocol. Sorry, and transport layer protocols. Okay. So today we are going to start with network layer, its functionalities, and what are the protocols that are related to it. Okay. So basically we will see or we'll understand the principles behind all the network layer services. So they'll be focused on two things, data plane and control plane. Before that, I will definitely let you know what is data plane and what is control plane. Okay. So we will talk about network layer service models, differentiate between what is forwarding and what is routing, how a router works, what is IP addressing or different ways of addressing basically, whether it's IPv6 or IPv4. Then we'll get into generalized forwarding and the internet architecture. Okay. So some implementation of protocols like IP protocol, NAT. We will see if we are going to get into middle boxes or not. That I will see later on. Okay, but definitely IP protocol and NAT is going to be taught in this course. All right. So in this chapter, we are going to look at the data plane part of network layer. Okay. So before that, we will get into what is data plane and then what is control plane. What else we'll look into? We'll look into, so when we are talking about the data plane part, this part will come into picture, that is what's inside a router. Okay, so we will see different functionalities of the input ports, output ports, switching in the router, buffer management, scheduling, etc. Then we will get into the internet protocol, which will where we will talk about datagram format, addressing, network address translation, which is NAT, and IPv6 also. Okay. Now, since we are looking into the data plane part, we will just start or give a little bit of overview of SDNs, and I'll see if middle boxes can be added here or not. But definitely a little bit of SDNs in the data plane, and then in control plane, definitely we have to anyways look at SDNs, that is software defined networking. Okay, all right. So as I already told you earlier also, this diagram is going to be our base diagram always. Okay, so until now we have done up to transport layer. Today we are going to start with network layer. Okay. Now, network layer functionalities, when we are talking about, at that point of time, we are just not concerned about a transfer of data or just the protocols at one host to another host. We are not going to look at only the edge systems basically. We are also going to look at what's going inside the network, right? Because they are also involved in these network layer functionalities. That means, so these are routers, right? So they also have network layer functionality. So when we are talking about network layer services and protocols, we are basically looking at what are the protocols, what are the services that will be um, provided at each of the um, nodes present in this diagram. So all these nodes, either it can be an end system or it can be an intermediate router in between. Okay. So at the end systems, of course, we have all the layers and corresponding protocols up to application layer. Whereas in case of routers, we have it only up to the network layer. Okay. So what is the task that we are going to look at? Okay. So at the sender side, what will happen? segments are encapsulated into the datagrams and then they are sent to the link layer. Okay, so this is what's happening. So suppose this is a sender, this is a sender. So whatever segment is being received from the transport layer in the network layer, that segment is encapsulated into a datagram and then it is passed on to the lower layer, which is the link layer. Okay, and what happens at the receivers I mean at the receiver's end, just the opposite will be happening. That means from the link layer, okay, the network layer will receive the frame, get to the datagram, it will take whatever information is needed, it will decapsulate the segment, that is, it will just get the segment from the datagram and then move the segment or deliver the segment to the corresponding transport layer. Okay, so it will be moving the segment to the transport layer, okay, at the receiver side. So these are the tasks corresponding to network layer protocols corresponding to a sender and a receiver. So now what happens at the routers? Okay, at the routers we know that we have only these three layers: the physical layer, link layer, and the network layer. Okay, so what are the tasks that the router will do corresponding to this layer? So first thing is it will examine the header fields in all IP datagrams passing through it. Of course, it will require to check it in order to just find out that what is the source or destination address and other information also, which we will look into in this chapter itself. So just for the sake of it, just out of the common sense, we can say that okay, it just examines the header IP fields in all IP datagrams passing through it for simply knowing that what is the corresponding IP address. Okay, then it moves the datagrams from input ports to the output ports. Okay, of course, when you get to know that um, an incoming packet is having a particular IP address, then after that, by doing some kind of calculations or by seeing some tables, the router will actually decide that which port it has to send the particular datagram. That means which output port it has to send the particular datagram to. So that is another task. And also it finds out what is the end-to-end path for a given datagram. Okay. So if you remember the first chapter when I had told about forwarding and routing, right? So at that time I had told that there are two tasks. One is that which output port the datagram has to be sent, and another is that what is the entire path that this particular datagram which has arrived to a particular router, what is the path that this datagram going to follow in order to reach from the source to the destination, and that is called as routing, right? So it also finds out, so the router it has the functionality to find out what is the end-to-end path. So as I already told you, there are two key network layer functions. One is forwarding and another is routing. Okay. So what is forwarding? It moves packets from a router's input links to the appropriate output link. And what is routing? That is determine the route that a packet needs to take in order to be sent from the source to the destination. Okay. And the route is determined with the help of various routing algorithms. Okay, so in this chapter we are going to study a number of routing algorithms also. Okay, so this is going to be a very interesting chapter. You are going to get to know as to how everything works at the core level, okay, in the core network. So I would suggest you to please pay attention to this class properly. I mean, this entire chapter, because this is going to be very, very interesting and it is a very, very important chapter also. Okay, all right. So, this is a simple analogy. I think you already have that information with you. But, anyways, I'll just repeat here that forwarding means that is just getting out of one interchange. That means just telling the router is just going to tell that which output port the packet has to move towards. Okay, that is, if a packet has been received at a given input port, which output port should that packet be forwarded to in order to reach its actual destination. That's what is forwarding. And routing is, of course, you plan for the entire trip from the source to the destination. Okay, so you need to know what is the exact route from the source to the destination. These are the two differences. So now I have been talking a lot about data plane and control plane. I told in the beginning slides also that we are going to see functionalities related to data plane and control plane. Okay. So data plane is nothing but, it is a per router function. It is a local function that happens in the router. Now, if you have paid attention, you would know that, what would be the local function for a router. Just to move the packet or the datagram from the input port to the output port, right? That means forwarding comes under data plane for functionalities. Okay, like here it has been given in this diagram. So there's a packet with the given header 0111. So the router's job is to read the header to find out that what is the given destination address, and according to this destination address, which output port the packet needs to be forwarded to. That functionality comes under data plane functions because these are local to the router. Okay. Now, what is the control plane function? It is a network wide logic. That means some task that is dependent upon how the entire network has been laid out, right? So what would that be? That would be routing, right? So how a datagram should be routed among different routers which are there along the path from the source to its desired destination. Okay, so determining this path is known as a control plane function. Okay, so these are the these are basically how it differentiates data plane functionalities and control plane functionalities. So there are two control plane approaches. One is, you find out the path using traditional routing algorithms, which are generally implemented in the routers itself. Okay, in the individual routers itself, you will have different routing algorithms through which you could find out that, okay, what is the um, path from a given source to a destination for a datagram that has arrived. And another approach is software defined networking. Okay, I am pretty sure you might have heard about this by now. Okay, so software defined networking is a concept which is used so that you do not have to implement these routing functionalities in each one of the routers. Okay, you can implement these functionalities in a remote server and then you can work with that at each of the routers. So we will also read about this SDN in this chapter itself. Okay, but first, so this network layer chapter has been divided into two modules. Okay, one is your data plane module, another is your control plane module. First, we will start with the data plane module. Okay, now just because I talked about the control plane module also, and I have already talked about the traditional routing algorithm and SDN. So I am just going to show you that how the per router control plane works. Okay. So here what would happen, that individual routing algorithm components will be there in each and every router in order to interact in the control plane. So that's what I told, that if it is a per router control plane functionality, that means at each router you are going to have certain routing algorithms which are going to help to find out the desired path from source to the destination. So this is how it works out. See, as I have told you. So you have this header field here, and that is checked. So you do have a functionality at the router, and you also have local forwarding table at the routers, and then correspondingly you find out the destination as the path to the destination and also the corresponding output port. Okay, so the control plane functionality would be just to find the path from the source to the destination. Alright, so that is done with the help of the corresponding routing algorithms, which are there as a functionality in each individual router. Okay. Now, whatever output you are getting from the routing algorithm, that means if you know the path or if you get to know the path, only then you will get to know that what should be the output port that a given datagram has to be forwarded to in order to reach its destination. That information is added at the local forwarding table. Okay. So using whatever output you receive from the routing algorithm, it can be used to forward the data, and then the datagram can be transferred to the corresponding output port. So this is the differentiation that is made. So these are the control plane functionalities and these are the data plane functionalities. Now we are going to look at the SDN plane. Okay, SDN control plane. So as I told you, what does the SDN do? Instead of each router having individual functionalities for calculating the entire path using different routing algorithms, what can be done is that a remote server can be there which can compute and install forwarding tables in the routers. So what is it? So this is how it works. Okay, so you do have remote servers which remotely controls all the forwardings at the different routers. So how does it do that? It has the corresponding forwarding tables and there is continuous interaction between each of these routers and the remote server here in order to find out that if a datagram has reached, what should be the corresponding output port. Okay. So here too, you have a control plane and a data plane segregation. So at the data plane segregation, of course, once you get the information that is locally sent back to the individual router, and from that, the datagram can get to know that, okay, what if from the given forwarding table index, the datagram can actually find out that what is the corresponding output port that it has to be transferred to, and then it is transferred to the corresponding output port. Okay, so that is the data. So the forwarding is the data plane functionality, and at the control plane, the remote controller basically computes that given the um, destination address, what's the path and what should be the corresponding forwarding table entry, and then that is transferred to the corresponding routers. So that's the control plane functionality here. Now, the question here is that what is the service model for channel transporting datagrams from sender to receiver? Okay, so what are the basic features that should be provided or services that should be provided for transporting datagrams from a sender to a receiver side? So first thing is that there should be guaranteed delivery. Okay, guaranteed delivery and within a bounded time. Okay, these are some examples of what kind of services one might ask for. Okay, so depending upon the kind of application the user is basically asking for, there are several features that a network layer protocol or network layer service must provide. One example is that there should be guaranteed delivery. Okay, so for certain kind of applications, it is necessary that guaranteed delivery of data should be there. For certain kind of applications, it is necessary that on top of guaranteed delivery, it should be there or the packet should reach within a given time bound. Now, what are the services for flow of datagrams? Okay. So first is in-order datagram delivery. That is one example service. Another is that there should be a guaranteed minimum bandwidth to the flow. That means whatever data is being transmitted, it should get or it should be transmitted with some minimum bandwidth. Okay. And the other one is that there should be restrictions on changes in inter-packet spacing. Okay. All right. So let us see some of the example applications here. So let us talk about the best effort service model. Okay, just a second. Excuse me. Okay, so network layer service model. So this is just a table that we have put here. So what is the network architecture? What is the service model that it provides? And then what are the different QoS guarantees that this particular service model is providing for the given network architecture? Okay, now we have already, I had already told you about the term best effort in previous classes. If you remember, then you would know that best effort service model, it just simply means that your provider is just telling you that I will do my best to transfer your data or to deliver your data to the given destination. I will not guarantee anything. That's what your service provider will tell you if the service provider is providing best effort. So let us see what are the QoS guarantees that it provides. So as I already told you, the provider does not take any responsibilities. Okay, so there are no QoS guarantees when it comes to best effort service model, as you can see from the table. There's no bandwidth guarantee, there's no packet loss guarantee. That means, there should be no loss of packets. That is not guaranteed at all. There's no in order delivery, and of course, timing is also not a guarantee. Okay, but the internet uses best effort service model. So why is that so? All right. So as you can see, it has been just simply given that there's no guarantee on successful datagram delivery to the destination, no timing or order of delivery guarantee, no guarantee on the bandwidth that would be available to end-to-end flow. Okay, so there's no guarantee that best effort service model provides, but in the internet, best effort service is the one that is mostly used. Okay, now we will see some other network architectures which provide different service models. Okay, so as we know, internet, the first point we have already done. So internet uses best effort service model and gives no QoS guarantees. Next network architecture is ATM, that is asynchronous transfer mode. Okay, so this is a different kind of network architecture which uses, some concepts of packet switching as well as circuit switching. All right. So we will see to this if we have time at the end of this course. This is a different kind of network architecture. Now we are looking at internet only, so we will see how the layers are working in the internet network architecture, whereas ATM is a separate kind of a network architecture. So if you're interested right now itself, you can go and check out, ATM and these different service models that it provides. Okay, constant bit rates and available bit rates. So these are nothing but the CBR and ABR, that is constant bit rate and available bit rate. These are nothing but that how much of data rate is being provided for transferring the data. Okay, so as you can see that for constant bit rate, the bandwidth is of constant rate. So a constant rate bandwidth is provided for end-to-end delivery or end-to-end transfer of the data or flow of the data, sorry. And there can be packet loss. In order delivery is provided though, and timing bound is also provided in the CBR kind of service model. Whereas in ABR or available bitrate, what is the available bitrate kind of service model? So in this one, some minimum bandwidth guarantee is given to the user. So that means if uh, I purchase some data pack and from the service provider will guarantee that minimum maybe you will get some 50 kbps of data rate. Okay, so that's the available bitrate kind of service model. So so here too there is packet loss, and then you have in order delivery of data, but there is no timing bound here. Okay, I think I said that in constant bitrate packet loss is there, but actually packet loss is not there. Okay, so in CBR packet loss is not there, whereas in ABR packet loss is there. All right. Now, internet, there are two different service models again, that is in-serve guaranteed and diff-serve. Okay, so what is this in-serve and diff-serve? Okay, so these are basically different types of service models which are dependent upon what is the bandwidth demand from the user side. Okay, so in-serve is the one that basically takes care of how the sorry, diff-serve takes care of how the different applications are basically asking for different bandwidth guarantees, whereas in-serve does not guarantee any such thing. Okay, so it just gives out a particular amount of bandwidth guarantee. So that is what is given here in the QoS guarantees, that you have a bandwidth guarantee, no packet loss, in order delivery, timing bound is also provided. Whereas in diff-serve, bandwidth guarantee may be given, possibly loss may happen, in order delivery may or may not happen, but there is no timing bound. Okay. So given all of these, services that you have, service models and their properties that you have seen, one might think that if you just look at this table, you would see that none of the guarantees are provided by the best of our service. Then why it is even there? It shouldn't even be there, right? Why? But if you get to know the internet, you will see that most service providers for normal customers, it provides best effort service. And why is that so? There are a few reasons. First of all, that it is a very simple strategy. Okay, so there's no headache for the service provider. Only headache that the service provider has is that it has to try to transfer the packet. Okay, so that's the only headache. So least amount of headache in this case. So simplicity of mechanism has allowed the internet to be widely deployed with best effort services. Okay. Now, because sufficient provisioning of bandwidth is done at each links, that allows the performance of real-time applications to be good enough for most of the time, even if best effort service is being used. So basically, what it says is that if you do have a good provisioning of bandwidth in your link, that means if you have a good link capacity, that will anyways allow a good real-time performance, right? For some real-time kind of applications like interactive voice, video, etc. So if you have a good enough performance, it is okay for an average customer in general. So that is why, because it is simple and it gives a good enough performance, it is used widely. And what is the third one? That is, it is replicated application-led distributed services, okay, such as data centers, content distribution networks, etc. So what it does, connecting close to clients' networks and allows services to be provided from multiple locations. Okay, So basically, what is this? If you have a simple mechanism and you are providing a good enough service, you can actually think of complicated services which are basically distributed services like data centers, content distribution networks, etc. So what's done? Connecting close to the client's networks such that it allows the services to be provided from different locations. What's the fourth one? That is, it provides condition control of elastic services. See, we have already studied that how congestion control can be done from each of the um, receiver's side, right? We have already seen that. So congestion control can be done either from the network side or it can be done from the receiver side. So the different congestion control mechanisms actually help to give a best effort service. It's an improved service basically. So even if there is a congestion in the network, because the functionalities are available at the host side to actually control the congestion, it makes or it makes a simple process good enough for most of the time. Okay, so because of all of these properties that best effort service provided, or I would rather say that despite all the properties that or features that best effort service does not provide, still because of this simplicity and just because given the bandwidth, it most of the time gives a good result. um, it is unarguably the best one that is used or has the maximum success rate on the internet. Okay, so this is one here. And okay, so before starting with the data plane or the control plane, we need to first understand where it all works, right? So we will start with the architecture of a router, how a router looks like from the inside. Okay, so in this module, let us see how the router architecture basically looks like. Okay, so this is a very high level generic view of a router. You have a set of input ports, you have a set of output ports, right? So if you see your diagrams, you know that a router is connected with multiple connections. So let us have a generic view of it or a high level view of it, that there are a set of input ports and there are a set of corresponding output ports. What's in between we need to know, okay, in between the input ports and the output ports and how they work. That's also we need to know. But if you see these ports, input ports as well as output ports, you will see that there are certain boxes made here, right? These boxes basically represent different functions of each of the layers, different functionalities of each of the layers. Okay. Now, what we know in case of routers, only up to network layer functionalities are provided. Alright. So this is what will be there in between. That is, you have the input ports, you have the output ports, and in between there is a there is a small hardware part which is known as a high speed switching fabric. What is the task of this switch fabric? The task of this switch fabric is to transfer any datagram that is received at the input port to the corresponding output port. Okay, why it is required to be high speed? Of course, because you want, so there are so many input ports and so many datagrams are also arriving at these input ports. So you would want a very fast transmission of the datagrams from the input port to the corresponding output port. Okay, what else is there? This is the routing processor. Okay, which basically will give the information of, you know, which output port the given datagram should be transferred to. Alright. Now, given this generic view of the router architecture, what we need to find out that what are the control plane properties, what are the data plane properties. So up to the routing processor, as I told you, from here we get the information that what is the path and correspondingly what is the output port to which the corresponding datagram has to be transferred. So what are the tasks this routing processor will actually have to do? Routing and management. Okay, so basically some software functionalities which operate in very least amount of time, that is in milliseconds time frame. Okay, so this is the software part here. All right, so all the control information is here. Now the data plane part where actually the forwarding of the data happens. Okay, so it is related to the hardware. We already know that we have these input ports and the high speed switch fabric, which is responsible for forwarding the data from the input port to the output port, and with minimum amount of time, that is the time frame is of nanoseconds. All right, so this is our router architecture. Now take a look at this once more. In the input port itself, we have these boxes. In the output port also, we have these three different boxes in three different colors. And I've already told you that these represent different functionalities that are to be implemented on the datagram that is arriving or going out of the output port. Okay. So now we are taking a look at the input port functions. Okay. This is the input port and this is the corresponding switch fabric. Whatever datagram is arriving, there will be some processing done over here and then it will move to the corresponding switch fabric. Okay, what are the processes? So the first module, that is line termination. It is a physical layer functionality where what is done? Bit level reception of the data that is arriving. Okay, so this is a physical layer functionality. Then what we have? We have the corresponding link layer protocol at the receiver's end. So input port function means the router is actually acting as the receiver end for the datagram, right? So corresponding link layer protocol, for example, Ethernet. Okay, Ethernet is also a link layer protocol. We will read about it in the next chapter. Then comes the network layer functionalities. Now it is a data plane functionality we have already seen. So what are the tasks that will be here? First of all, lookup. That means look up in the table as to what the corresponding output port the datagram has to be forwarded. Once that is found out, you forward the datagram. So that means forwarding is one of the tasks. And if a large number of datagrams are arriving very fast as compared to how fast the switch fabric can transfer the data to the corresponding output port, then the datagrams need to be queued, and that queuing is also happening here. Okay. Now, decentralized switching. What is it? That is, you use the header field values, look up the output port using forwarding table in input port memory. Okay. What is the goal here? That is, you complete the input port processing at the line speed. Okay. So I just told you that the network layer functionality that happens here is that first the lookup is done to find out that what's the corresponding output port where the datagram has to be forwarded, and then it has to be forwarded to the corresponding output port. So this task is called as the decentralized switching, where you use the header field values, look up the output port using the forwarding table, which is there in the input port memory itself. Okay. Now, what's the goal for having all of this input port and the switch fabric? So, what should be our ultimate goal? Okay, the ultimate goal is that whatever the speed that is provided, okay, which is known as the line speed for the input port. Okay, so whatever capacity, let us call it as the capacity, because it is actually the capacity of this input port, right? So the goal is that all of these tasks should be completed at line speed. Okay, so whatever the lines, whatever the capacity this input port is providing, all the tasks need to be finished with the given line speed that is provided by the input port. Okay, now if that is not possible, then queuing will happen. That means when datagrams arrive faster than how the switch fabric can forward the datagram to the corresponding output port, in that case we will have queuing at the input port. Okay, now there are two ways of forwarding. One is destination based forwarding and another is generalized forwarding. Okay, so destination based forwarding is the traditional way of forwarding where you forward the data based on just, you check what is the destination IP address. You find out in the forwarding table that whether there is a corresponding entry for that or not, and then find out what's the corresponding output port. Once that is done, the data will be forwarded to the corresponding output port. So that's what is destination based forwarding. Then we have generalized forwarding. So that is like, you just simply look at the header field and simply find out that, okay, uh, depending upon any set of header field values, you simply forward the data to a particular output port and then just hope that I have done my job. I have forwarded it to the output port. Now the output port functionalities will take care of sending the data to the destination. Okay. So here too, it's basically like no responsibility is being taken in the generalized forwarding. Only the only thing that generalized forwarding helps us is it does the job faster, because it's, you will see in the later sections that, reading an entire IP address and then finding out the best match, what would be the corresponding output port, that actually is a time consuming task. So if you are not doing that, you are basically reducing on the amount of time that it takes to do so. Okay, so since I was talking about that, this is the one that we are going to see. Okay, when we are doing a destination based forwarding, what happens in that case? Okay, so this is how a typical forwarding table looks like. Okay, so here what we can see is that the destination addresses are divided into different ranges. So you see, these are IP addresses. Okay, and this is a range that is given here. Now given this range, you can transfer the data to the corresponding link interface. That means this is, if your packet, you check, if in your packet you check the header field to find out that what is the destination address. If the destination matches or falls in this range, then that packet has to be transferred to output port 0. If it matches the second one, then the data has to be sent through output port 1, and so on and so forth, depending upon what range it falls under. Okay. Now this here is assuming that all the ranges are known. Okay, and there is a default one that is, otherwise if it does not fall into these ranges, then the link that will be used is 3. That means the output port link will be 3, and through that the datagram will be transferred. Okay, but what if this is not done? What if this kind of a categorization is not done at all? So in that case, how to move forward? Okay, how to actually transfer the data to the corresponding output port? All right, so see what was happening here. Okay, we have this as a range. Okay, now in this, look at this part where you have this 100 and 111 as a range, which actually falls under this category, that is output port number 3. Alright. So these will be certain issues that will come under, even if you have it in a range, if you do not put the division properly. Okay. So in that case, how will you transfer the datagram to the corresponding output port? Okay. Now, as I was telling you that, one is that categorization or division of such ranges is a difficult task, or it may not be there at some point. But the one that I started with was that, see, these are IP addresses, and reading the entire IP address and then finding out that, okay, what is the best one, or what is whether the range is actually, or whether it falls under a given range or not, whether the corresponding output is actually listed in the forwarding table or not. These are questions that come afterwards. But first, you have to read the entire data or entire IP address, right? So in order to make tasks much easier, but in order to make it much correct, okay, you want to send the data to the actual correct output port. Okay, so for that, what you want to do, that you want to send it to the exact output port. So you want to match as much as possible. Look at this example here. Okay, 100 and this 111. Okay, anyone could say that, okay, fine, let us not get into this. Maybe it will fall under the link interface 0, but it can also fall under, it's not exactly this. It can fall under the otherwise category, that means the category number 3. That means, see, if you do not exactly find out, or that, what is the exact match here, whether this actually falls under this range, these two IP addresses actually fall under the range of link interface 0. Okay, but they are also, see, in the otherwise category also, they can fall if you do not read the full one, right? So in order to, reduce all these confusions, okay, what can be done? That, okay, we will find out that which one of these IP addresses actually matches or has the longest match with the given destination address in the datagram. Okay, so what is done in the longest prefix match? So when you look for forwarding table entry for a given destination address, you use the longest address prefix that matches the destination address. Okay, so suppose this is a given destination address. Okay, so these are the ranges that are given, and if you have an IP address among all of these address ranges that have been given here, whichever matches the longest or whichever matches with the maximum number of bits in your IP address, that one will be acting as the longest address prefix. Okay, so for example, if you have this one, okay, what are the values here? So this is 10 triple 110 okay. Now which one does it match with? Can anybody tell this one? The first one, which one does this match with? Which link interface does this IP address match with?
I'm 0.
Yes. So this matches with 0 because it actually does not match with anybody else after 0001. Okay. There's a 0 after this, and for others it is 11. Okay. The next one, actually, I myself am unable to see. Okay. I think the, yeah, 000, 11, 000. Okay. So the third set is basically 000, 11, 000. So it can match link 1 also. It can match link 2 also, right? But what are we looking at? We are looking at longest prefix matching. That means what is the largest number of bits that it matches with your given IP address. Okay. So in this case, we can go with interface number 1, right? So this is what I was talking about. Hmm. This is also a match and that is also a match. Okay. Wait, I have already talked about this. Okay. Now, why we should use longest prefix match, that we will see when we look at the IP addresses. Okay. What are the different IP addresses? But how do we take care of longest prefix matching? Okay. These are done with the help of some hardware devices known as ternary CAMs or ternary content addressable memories. This is when you take, or if you take topics in networks course in your next year. So in that case, or basically in the next semester, for the fourth years, not for you guys. So in that case, you can find out that how the ternary cams work, how the matching is done in that case. So I'll take that course and there you can find out. Okay, for now you just get to know that longest prefix matching is carried out at TCAMs or content addressable memories. Okay, because it does it faster. Okay, as you can see that it retrieves the address in one clock cycle regardless of the table size, and it can also keep a large number of routing table entries. Alright, okay. The next part is basically about switching fabrics. That is what is, how does a switch fabric work? What are the different kinds of switch fabrics? What's the basic architecture behind this just box that is given here? Okay, you've seen what is the input port going to do. We know what's the output port going to do. Okay, but what's happening inside this box? That's what we are going to study in the next class. Okay, this is going to take some time, so we only have 1 minute left for the class. So I will not go ahead with this one right now. If you have any questions, please feel free to ask.